So we're going to take a look at my hockey stick method here. And so we've got 4,620. And so what you can do is write it again. And I put a little L shape, which is where it gets the name hockey stick. I had some teacher at some point call it hockey stick. I don't know if they're a hockey fan, so I've called it the same thing ever since. And it can be a short L or not. But the key here is you're going to take and you're going to divide by prime numbers. Okay, so you're looking for a prime number that goes in here. So you can use your tricks that we learned at the end of the last lesson. Or what I like to do is whenever it ends in a even number, I like to keep working with 2. So I like to be very methodical and use 2 as much as I can. So I want to take 4,620 and divide it by 2. So 4,620 divided by 2, if I can do that for me, it's going to give us a 2,310. And then, like I said, I like to be methodical and keep using prime number of 2 as much as possible. So I'm going to divide by 2 again and get 1,155. So now 2 will not be a factor again. I've gone as far as I can with 2. So now I'm going to go ahead and, because it's ending with a 5, I'm going to use 5. So I divide it by 5, and I get 231. And 5 is not going to be a factor again because this doesn't end in a 5 or 0. So now I've got to find a different number that goes in, and because I see that 231 adds up to be 6 if I add the digits, I know that 3 is going to go in. So I'm going to divide that by 3, and we get 77, and 7 plus 7 is 14, so 3 is not going to go in, but I can see that 7 will, and I'm left with 11. As soon as your last number is prime, you stop. Okay, and so this is our prime factorization of 4,620. So in other words, if I take 2 times 2 times 5 times 3 times 7 times 11, we have factored completely 4,620. Okay, and this is a very useful technique to do greatest common divisors, greatest common factors, and least common denominators. It's a very useful strategy for multiple things. Simplifying square roots later, we'll do a lot with it. So here's the prime factors of 24. Of course, 1's always there. I just usually don't write 1 because you can multiply 1 at any time by any number. But if you break out the prime common factors of 24 and 40, what you'll see is as soon as you break it out, the greatest common divisor of them is the biggest prime factor, or biggest factor that they have in common here. So we're going to take a look at the greatest common divisor is the largest natural number that divides into both. And so if you're dividing by their prime factors, here we got 1, 2, and then 3, and so on, you're going to find the rest of the factors as you're working through. But greatest common divisor is the biggest number that divides into both of them. So let's take a look at find the greatest common divisor of 600 and 400 and 540. And so what we want to do is break it out into its prime factors. So notice how we've got 600 is broken up into 2 times 2 times 2 times 3 times 5 times 5. So in other words, if I had done my little factor tree technique, which is a hockey stick, then if I had taken 600 and divided it by 2, I would have got 300. Divide by 2, I get 150. Divide by 2 again, and I get 75. And divide it by 5, and we got 15. Divide by 5, and I get 3. These numbers right here are the numbers we're talking about right here. These numbers right here are the same thing you would get if you did 540. So the key here is, now check this out, is you've got the same amount. So if I circle a 2, 2. Circle a 2 here, circle a 2. That's all the 2's that this one has. There's a 3 here, there's a 3. This one has more 3's, but this one doesn't have any. This one's got a 5, this one's got a 5. These are the same prime factors that they have in common. See how they have those same prime factors in common? If I take these, the 2 times 2 times 3 times 5, and I actually multiply it together, so I get 4 times 3 is 12 times 5, gives me 60. What that means is that if these are the prime factors they have in common, then whatever that multiplies to, this is the biggest common divisor that they have in common. So if I take 600 and divide it by 60, you get a result of 10. If I take 540 and divide it by 60, you get 9. So it goes into both. 60 is the biggest number, guaranteed, that goes into both of these. So it's a pretty, this is a very useful strategy for multiple concepts in arithmetic. So let's take a look at another example here. Here we've got the least common multiple of 8 and 6, and what we can do here is do a prime factor tree for both 8 and 6. And so if I had done 8, I would have got 2, 4, 2, and 2. And then if I had done 6, I would have got 2 and 3. So if I list this out for 8, I get 2 times 2 times 2. And over here for 6, I got 2 times 3. So the way that this works, to figure out that the least common multiple of 6 and 8 is 24, is that I need to recognize that I've got 1, 2, 3 2s. So I need at least 3 2s in my least common multiple. And because over here I've got the 1, 2, I don't need to count it again. If this one had 4 2s, then I would need to add a 2. But this one has a 3, so I need at least a 3 here. And if you multiply this out, 2 times 2 times 2 times 3, you get the least common multiple of 24. So it's a very useful strategy to do this prime factorization technique. Let's check out another example. Let's go back to our 600 and our 540. So here's our prime factors using the same hockey stick. Again, the hockey stick would have worked to give us our prime factorization. But here's the key. The key is, if we recognize I've got 1, 2, 3 2s, I need at least 3 2s in my prime factorization. So 2, 2, 2. And here, over here, I've got 1, 2 2s. If this one had 4, then I would add another one. But you cross out the ones that you've already counted, and it doesn't have any more 2s, so you don't add to the list. So I got 1, 3 over here, so I'm going to add a 3 to the list. Over here, I can cross out a 3 because I've counted 1 from this guy. But then there's 2 more 3s, so I add 2 more 3s to my list. So I cross those out now because I've used all 3. So in other words, I have at most 3 3s. Here I only have 1, so I have down here 3 3s. So here you can see that I have 2 5s, so I put 2 5s on the list. And over here there's only 1 5. If there was more 5s, then if there was 3 5s, then I would add 1 to the list. But I cross out whatever they have in common, so I have the 1 5, and I've already counted 1 5. So then this leftover result is all the prime factors that the two of them, if I combine them and I took a balance of both of them, this is what I would need for each number to be the same. And so if I actually multiplied those out, that would give me my least common multiple of 600 and 540. And if I multiply that out, I get 5,400. And that is your least common multiple of 600 and 540. So let me do one more, and hopefully this is getting clear. So if I say, what's the least common factors of 10 and 25? Okay, you do your prime factorization of 10, which is going to be 2 and 5, and 25 is 5 and 5. So what I need is a 2. I need 1 2, at least 1 2. This one doesn't have any, so I don't need to do anything with it. This one's got 1 5, so I'm definitely going to need a 5 down there. But this one has 2 5s, so that means in my result I'm going to need 2 5s as well. So you need a balance of as many of a prime number as you have over here. You have to have at least that many prime numbers on the right side. Whatever it doesn't have, you add it down. So if I multiply 2 times 5 times 5, so in other words, 2 times 5 is 10 times 5, 50 is the least common multiple between 10 and 25. So I hope that that's clear for you. be a very nice process. So let's take a look at this problem. You've got a bullet train that just departed from Tokyo, Osaka, and I'm not going to keep reading the names, and they depart every 90 minutes. The other train departs every 120 minutes, and the last train departs every 80 minutes. The question is, when will all three trains again depart at the same time? So the real question here is trying to find what is the least common factor, least common multiple, factor multiple of these three times, 90, 80, and 120. And so if I take and break these down into their prime factors, we would get 90 is 2 times 3 squared. In other words, there's 2 3s times 5. 80 is 4 2s, 2 to the 4th. There's really 4 2s right here. And then here, 120 is 2 to the 3rd times 3 times 5. And so what we can do is recognize what they have in common. And here we have, here's an easier way of saying what I was saying earlier, is the greatest powers of 3 and 5 is 3 squared. Notice over here there's 1 3, but this is the greatest power of 3. Here's a 5, and they all have 1 5, so the greatest power of 5 is just 1. The greatest power of 4, the most 4s that you have is this one, 2 to the 4th. And over here we've got 2 to the 3rd. That's a little smaller than this one. So if I take the greatest powers of each, that's an easier way of saying what I was saying, and multiply the greatest power of, or greatest quantity of my prime numbers, and I multiply it out, that will give me the least common multiple of the three numbers. So it's the greatest amount of prime numbers that you have in any one particular factorization. That's the one you want to use down at the bottom here. And of course, that's 720 minutes, and so every 12 hours is when all three trains would depart at the same time. Okay, so that's the end of this lesson. If you have any questions, please email me through the Ask My Instructor feature of the lab.